company Instacluster. Today we'll be covering open source solution engineering using multiple open source technologies and the best practices and approaches you should take in all these various technologies. So, there, no hat. Now I'm sure everyone out there is not getting haircuts, so we're all developing some unique looks. So what is Instacluster? Well, I will tell you, we're a one-stop shop for 100% pure open source technology. So nothing we offer or sell or support is a licensed product. Let me say it again. Everything we do is purely GPL3 or Apache 2. So that's basically our entire business model is around support and professional services around open source technologies. So we have three arms to our business. We have a managed platform, which means you can run various open source technologies on our managed platform, such as Kafka, Cassandra, Elasticsearch, Spark. Now we also have Redis support. So we'll support a wide range of open source technologies via ticket-based support and remote access if that's required. And finally, we have consulting and experimental labs. I'm part of the consulting arm. So what is the consulting arm? Well, basically what consulting looks like is we look at your environment, we determine different ways in which we could optimize that environment, and then we provide a lot of bespoke trainings, workshops, and finally migrations from existing proprietary solutions or legacy products to a pure open source solution. So what is consulting? Well, basically it's a one-stop shop for everything starting from strategy to the architecture, development, implementation, then training in that implementation, finally support, then after we could just manage everything for you. So we could go from strategy to planning all the way to support and production implementation. The differentiator between us and a lot of other companies is we have deep expertise. For the past 2 years, I've been doing literally nothing but Kafka. That's all I know. That's all I care about. If you spoke to a lot of data engineers, they probably know like 20 different technologies. I'm not that kind of guy. I just know Kafka. That's it. So we have deep expertise. We have thought leadership. And, we do a lot of blogs, a lot of contributions. We write scripts. We are open source contributors as well to various projects. There's about 150 of us worldwide. I'm based in Redwood City, California, so in the Bay Area. If anyone wants to meet and have coffee, wearing a mask and a face shield and hand sanitizer, I'm definitely down. I'll also have to be 6 feet away, of course. We have also customers all over the world, from the retail, the finance industry, to sensor data, technology, etc. So something about the instructors, I'm Zeke, I'm your Kafka teacher, so I just do know nothing but Kafka. That's all I do, that's all I know. I literally eat, breathe, and sleep Kafka, so that's all I think about. And why do I get excited about Kafka? Well, I'll tell you in a bit, but that's what I do. Then we have Adam, who's the co-founder of the company, who works primarily on Cassandra, and Musa is our resident Elasticsearch expert. Musa also knows Kafka, and he and I kind of are building this data pipeline model where you ingest everything through Kafka and then you pump it into Elasticsearch for, analysis and data science. So again, at a glance, Instacluster is your one-stop shop for pure, unrestricted, license-free, open source software. So what's the agenda today? Well, we're not covering Cassandra. We will have it in the lab, but I'm not covering that in the subject at all. If there's time, maybe I'll run some slides on it. We'll mostly be covering just Kafka and Elasticsearch today because we're working on various data sources, and we're going to be doing a lot of data transformations in Python. And we're going to be doing some SQL as well. Now, I'm not sure how much SQL we'll be doing, but it's part of the agenda. Now, before we get into the slides, I would like it if everybody could go to this link in the window. I'm going to type it in the chat box right now. I would like everyone to download the source code and get the Docker containers up and running. And don't follow any of the instructions except for getting the Docker environment up. So just git clone that link and then I want you to do Docker compose up, and then I also want you to follow the instructions on setting up Python 3 in the COVID-19. But for now, focus on getting the Docker environment up and running, because that could take a long time, because you're downloading dependencies and binaries, etc. So I'll give everyone a couple seconds to acknowledge the link in the chat box. 30 seconds. All right, 15 seconds was long enough. Sounds like someone got it. One person's good enough for me. Let's get straight into Kafka, right? Let's do some Kafka stuff. How's that sound? All right. So I need to. Okay, everyone can see my screen, right? Awesome. Now everyone sees my screen, not speaker notes, I'm hoping. Awesome. Well, here we go then. Let me just go to the next slide. So why Kafka? Why did someone even think of the need for Kafka, right? That's kind of something important to know. So basically, there was this thought leadership around this idea of microservice. And a microservice is essentially an example of where you take a big monolithic web application that does, say, everything you want it to do, and you split it up into a number of other processes that you can pick up discrete business logic functions, say maybe authentication, logging, user management. Yeah, I guess, Craig, I'm not a curl or wget expert. I just run the commands. The main point is you have to download the jar files, but I'm not really too worried about the jar files. I'm more worried about the Docker stuff. Getting that up and running might take you several minutes. So a microservice is basically, a way of breaking up discrete business logic into solvable chunks, right? Where you have a microservice that solves one very specific thing and you put it in its own application, and those different microservices can communicate. And since they're going to need to do that, they're also always done via HTTP, where they have defined APIs. So essentially, the difference between a monolithic architecture and a microservice architecture, on the left-hand side, you can see the monolithic architecture, where you have what's called a three-tier typical architecture. We have the UI layer that the user interacts with. They click on stuff on the screen, which happens to trigger functions inside your business logic, which then uses the data access layer to communicate to a single database that stores all of your data. And business logic is this giant beast that has everything. This would be called the LAMP stack. Anyone here remember LAMP stack or Oracle or any of that giant stuff, where you basically just have a giant server? So in a microservice architecture, you still have one user interface that the user interacts with, but these actually trigger independent microservices, which could have a shared database, or maybe they could each have their own database and they'll do only one very specific function. So you have the user interface layer, business layer, data layer, and the microservices, where everything is discretely broken down into solvable chunks of data. So the advantages of microservices. Well, microservices provide fast value delivery, which means that we can fix the component of a microservice easier if we know that we can release and run it independently. We can implement the new features faster because, we can just put in one component and it doesn't affect the rest of the whole topology. We can run experiments like all of a sudden we need new features and we want to validate the assumption feature. This is super valuable that allows businesses to grow. And basically it's where you can move from a cost center to a value producer, right? Because now that everything's independent, you don't have to worry about, double efforts. You can spend a lot of time writing features rather than testing features. And there's less spaghetti code. A microservice, by its design pattern, doesn't allow you to just reference different data models, different databases, different systems. That's simply not possible. Microservices actually increase the confidence in the development process because we can fix things easier, that we can add a feature easier, and so on. It means it's a big major attraction towards. Can everyone hear me okay? Okay. Has the audio quality changed at all? It has changed? Okay. How about now? That should be much better. How about now? Perfect, yeah. It was using my laptop speaker, so sorry about that. All right. So, by the way, if you have any questions, put them. Yeah, I can't tell you what to do. You can use the chat room, or you could use the question and answers. I'll answer both of them as I see the questions live. So, it should be good. So microservices are language independent because these microservices communicate via HTTP. It doesn't matter what language is happening on the back end as long as they conform to HTTP standards so they can communicate. Or maybe one microservice is written with another, which is written in Java, something else is written in Python, it doesn't really matter. But the point is that it's a distributed architecture that's purely HTTP based. Another advantage of microservices is it allows you to split up each microservices into its own team. An ideal workplace of a monolithic architecture, you'd have, let's say, 30 people working on this big project, and it's big, it's clunky, and you spend about 80% of your time testing stuff. Who wants to test stuff 80% of their time? Well, nobody. Nobody wants to do that. So with microservices, what you do is you deploy a self-contained solution that can mock all the other microservices, and then you connect to them. And you're able to perform isolated acceptance and testing and all this stuff. And yeah, you focus on a very specific business function, and the other teams don't care what language you're using. There's a serious separation of concerns, and you have a loosely coupled architecture. So there's no spaghetti code or interdependencies. Microservices also isolate faults and exceptions inside your program. So if one microservice fails, it doesn't necessarily mean that the entire application fails, especially if you're practicing like a RESTful API. RESTful APIs in one microservice can handle one microservice failure and respond accordingly to the user through the user interface. It doesn't have to crash the whole system, right? If you're having a monolithic, something breaks, everything else might break. Cascading failures, you don't want that. Microservices work really well with containers. You can containerize a single microservice, which then makes it scalable. And it is really one of the biggest advantages to microservices is that they are dynamically scalable at runtime. When using cloud computing, it's so important to do on-demand pricing is to scale elastically. So the major benefit of a microservice is you can scale horizontally as you need to. So let's talk about event-driven architectures. When we were looking over here is what's called an event-driven architectures, and these really are self-contained units that talk to each other over either queues or topics. That's the kind of thing you can implement using messaging middleware, where different microservices are decoupled and speak using the message bus. Typically, there are a large number of producers and consumers in streaming applications. The key challenge here is to make sure that the message evolves to keep track of this model. This is where things like Kafka come into play. Let's talk about Kafka. Like, why was it invented? Well, Kafka was invented at LinkedIn in around 2008 when they realized that they had, different dependencies linked at various different points. People were injecting dependencies. I don't know if you guys were doing .NET in the early 2000s, but you would like inject dependencies. Dependency injection is horrible. Don't remind me that. It's horrible. So the problem they noticed was that they're basically linking systems ad hoc, willy-nilly in the code and requiring different systems, and they needed a centralized approach to this whole problem. So that's how they invented Kafka. They wanted a unified commit log, a distributed commit log, to merge all the data as needed. So what is Kafka at LinkedIn? Well, basically, LinkedIn has about 1,400 brokers. They process 1.4 trillion messages a day. And every message is Avro encoded, and they have multiple uses of this. They use it as a data bus, a message queue, database replication, metrics, logging, web application tracking data, and real-time aggregation. So Kafka's growth is exploding. More than 1/3 of Fortune 500 companies use Kafka. These companies include the top 10 travel companies, 70% of the top 10 banks, 80% of insurance companies, telecom, and much, much more. LinkedIn, Microsoft, Netflix process trillions of messages a day. Kafka is used for real-time streams of data. It is used to collect big data or to do real-time analysis or both. Kafka is used with in-memory microservices to provide durability, and it can be used to feed events to complex event streaming systems, or if this, then that /IoT style automation systems. Why Kafka? Well, it's fast, scalable, reliable, redundant, and you can do stream processing with it. Kafka is off, so basically you can do real-time stream processing of data like service calls, IoT sensors, etc. Kafka is a fast, scalable, durable, and fault-tolerant publish and subscribe distributed commit log. What that means is Kafka will distribute its data based on the partitions, and the more partitions you have, the more machines you have, the more scalable it is. So Kafka can scale exponentially, essentially. And it's much more scalable than message-oriented middlewares like RabbitMQ and traditional systems like JMS or Celery. Top 10 features of Kafka. Kafka is operational simplicity. Kafka is set up and to use, and it's easy to reason how Kafka works. However, the main reason Kafka is very popular is because of its excellent performance. It has other characteristics as well, but so do other messaging systems. Kafka has great performance, it is scalable, provides reliable durability, has a robust publish and subscribe queue system that scales to an infinite number of consumers. And basically, for the replication, producers have what are called tunable consistency guarantees, which means that your data is preserved at the shard level. Shards are keys in a cluster technology. In addition, Kafka works well with systems that have data streams to process and enable those systems to aggregate, transform, and load into other stores. But none of these characteristics would matter if Kafka was slow. The most important reason Kafka is popular is because of Kafka's exceptional performance. So Kafka works with Flume, Spark, Storm, HBase, Flink for real-time ingestion, analysis, and processing of streaming data. Kafka is a is the data stream used to feed Hadoop big data lakes. Kafka brokers support massive data streams for low latency analysis in Hadoop Spark. Also, Kafka streaming is used for real-time analytics. Kafka relies heavily on the operating system kernel to move data around quickly, which keeps the JVM heap size small. It relies on the principles of zero copy. Zero copy in Linux uses a send file to copy standardized byte messages to a page cache once, rather than following the buffer workflow. Kafka enables you to batch data records into chunks. These batches of data can be seen end-to-end from producer to a file system to the consumer. So batching allows more efficient data compression and reduces I/O latency between consumers and producers. Kafka writes to an immutable disk log sequentially, so it doesn't perform any kind of random disk access. So there's no searching involved with Kafka, unlike a database where you have to insert and update records. And this sharding, and this data is also sharded, so it's distributed among partitions in a cluster. So it's distributed evenly and horizontally. Let's look at Kafka versus a traditional messaging queue. So basically, traditional messaging queues discard the message after it has been processed from the end of the queue. Usually they're FIFO-based to consumers, just FIFO-based, reading from the head and processing the data sequentially. Traditional systems really do not allow you to replay events or stream the data. Kafka, on the other hand, is more a persistent storage. The reading of data and the storing of data are completely independent. So you can read the same data multiple times in Kafka. It really is just a distributed commit log, which happens to be used for things like messaging and streaming. But at the end of the day, it's a distributed commit log, which means every entry in the log is committed across the cluster and copied 3 times. Messages are replicated as well. So they're not copied once, not twice, but 3 times for 3 machines in the cluster. A cluster can handle multiple broker failures. Kafka is great in that it could work with just one of the remaining Kafka brokers surviving. It has very high throughput. It supports real-time data and batch consumption, and it can do data retention. Let's talk about use cases of Kafka, right? So you have messaging, you have metrics, you have website activity tracking, you have stream processing, event sourcing, and a commit log. A lot of large companies that handle a lot of data use Kafka. Kafka, where it originated, uses it to track activity data and operational metrics. Twitter uses it as part of Storm to provide stream processing infrastructure. Square uses Kafka as a bus to move all system events to various Square data centers, such as logs, custom events, metrics, and so on. Outputs to Splunk and Graphite. And this implements, complex event processing and alerting systems. It gets used by other companies too, like Spotify, Uber, Tumblr, Goldman Sachs, PayPal, Cisco, etc. So there is massive adaptation out there. You have LinkedIn, you have Twitter, you have Square, they're all using it. What is Kafka? It's so amazing. What is it? So like I keep saying, Kafka is first and foremost a distributed commit log, and it's used to publish and subscribe streams of messages, also known as records in Kafka terms. Kafka provides fault-tolerant storage as it replicates messages to multiple servers. Kafka is designed to allow your applications to process records as they occur. Kafka is fast, uses I/O efficiently by batching and compressing records. Kafka gets used for decoupling data streams. Kafka is used to stream data into data lakes, applications, and real-time analytics. So, as you can see in the above diagram, there is all these various applications. They were spaghetti code together. And once we introduce Kafka into the equation, it is much more streamlined, so to speak. Kafka fundamentals. Kafka consists of records, topics, consumers, brokers, and clusters. Records can have a key, a value, and a timestamp. Records are immutable, and a Kafka topic is a stream of records, such as orders, user signups. You can think of a topic as a feed name. A Kafka topic is a log, which is topic storage on disk. Topic log is broken up into partitions and segments. The Kafka producer API is used to produce streams of data records. The consumer API is used to constrain records from Kafka. A broker is a Kafka server that runs in a Kafka cluster. Kafka brokers form a cluster. The Kafka cluster consists of many Kafka brokers on many servers. A broker sometimes refers to more of a logical system or as Kafka as a whole. Kafka uses Zookeeper to manage the cluster. Zookeeper is used to coordinate the brokers and cluster topology. Zookeeper is a consistent file system for configuration information. Let's talk about Kafka messages. Kafka message is basically a unit of data. In Kafka, a message is known as a record. A message is a key value pair. All data stored in Kafka is as byte arrays. All data, a producer provides serializers to convert the key and value to the byte arrays. The key and a value can be any data type. The topic is a category or feed name to which records are published. Topics in Kafka are always multi-subscriber. That is, a topic can have 0, 1, or many consumers that subscribe to the data written to it. Each partition is an ordered immutable sequence of records that is continually appended. It's called a structured commit log. A partition is nothing but a directory of log files. The records in the partition are each assigned a sequential ID number called an offset that uniquely identifies each record within the partition, right? So on the left-hand side, you have your producers. In the middle, you have your topics. Topics are kind of a logical channel, like /users, /readers, etc. And consumers on the left-hand side, read the data. Let's talk about producers. Producers pushes messages to a Kafka topic. As each topic is divided into partitions and each write to a topic is handled by a leader replica, there are multiple brokers involved in writing to a topic. The producer directly writes to the broker, which holds the leader replica. The producer can use batching to send batches of records with efficiency. Producers can be written in any language such as Java, C++, Python, Go, and many, many more languages. You can also use it from the command line as well. Producers can be anything. They could be cars, they could be financial institutions, hospitals, or shipping. But the most important feature of Kafka is acknowledgements. Kafka will acknowledge that you've read the message either once or to all three brokers. So that's why it's a distributed commit log. The commit is distributed. Let's talk about Kafka consumers. Consumers pull messages from one or more topics. The consumer requests a micro batch of records. The broker uses the offset to provide the latest records to the consumer. The consumer offset is stored in a Kafka topic called consumer offsets. The consumer offset keeps track of the last message read. Because Kafka does not delete records immediately after they are read, consumers may reset the offset to provide a previous value to replay records, right? So you have a consumer which pulls the broker every X number of seconds to pull some data. The big difference between Kafka and other systems is Kafka is a pull-based system, not a push-based system. Kafka doesn't tell a consumer it has new messages to send the consumer. The consumer calls Kafka and says, hey, do you have any more messages for me to read? Kafka will say, yes, here are some messages. Or Kafka will reply, no, no more messages. And the consumer will go, okay, I'll check back later. And he'll check back again. Kafka consumers work exactly like sharks in the ocean. If they stop pulling Kafka or stop swimming, they will die and they'll be kicked out of a consumer group. So it's pretty important that a consumer application continually polls Kafka for new records. Let's talk about a topic partition and an offset, producers and consumers. So consumer groups remember the offset, which is the reading position where they last were left off. Consumers each have their own offset. Producers will always write to the end of the log. Remember, Kafka works sequentially. It's not searching in the middle of a log, it's just going to write to the end of the file. And consumers have a pointer. So there's no searching involved in Kafka. That's a very different operation. So consumer groups each have their own offset. Producers are reading to offset 12, while the partition 0, while consumer is reading from offset 9, and consumer B is reading from offset 11. Let's talk about brokers. Basically, a Kafka cluster is made up of multiple brokers. Each broker has an ID. Kafka broker contains a topic of log partitions. Okay, the one broker bootstraps a client to the entire cluster. And if you want to make your Kafka cluster resilient, you should have at least one Kafka server. Kafka cluster can have as many brokers as needed. Let's talk about Kafka clusters, failover, and in-sync replicas. Kafka supports replication to support a failover type operation. So you should recall that Kafka uses Zookeeper to form Kafka brokers in a cluster, and each node in a Kafka cluster is called a Kafka broker. Topic partitions can be replicated across multiple brokers for failover. Topics should have a replication factor greater than 1. For example, if you're running in AWS, you would want to be able to survive a single availability zone outage. If one Kafka broker goes down, then one Kafka broker, which is an in-sync replica, can serve the data. Zookeeper. So Kafka uses Zookeeper to do leadership election of the Kafka broker and the topic partition pairs. Kafka uses Zookeeper to manage service discovery for the Kafka brokers that form a cluster. So the Zookeeper sends the changes of the topology to the Kafka cluster, so each node in the cluster knows when a new broker has joined, a broker has died, or a topic was removed, or a topic was added. Zookeeper provides an in-sync view of the Kafka cluster configuration. So here's a diagram kind of overviewing what Kafka is. Producer, consumers, the Zookeeper cluster, which manages the configuration, the Kafka cluster, which is at least 3 machines, which each have 3 brokers. The producers write to topics in the broker. So you have topic A, you have topic B. And the consumers read from topics, usually in a consumer group. And depending upon the number of partitions available, that determines how many consumers can read the data. So this is the architecture of how Kafka essentially works. And you can use Kafka for many different applications. Any questions so far? Now is a good time to ask me some questions. Yeah, so a consumer basically subscribes to a topic and it will try to pull some records. And we'll look at some code later. I've actually published Python code, so it's very easy to understand how Kafka is working. But basically, it will pull a number of messages, basically however many Kafka decides to send it to, or how many you tell Kafka to send back. And it will pull the messages and then start processing them. And then after you finish pulling your messages, you commit your offsets. Did that clarify your question, or? Yeah, let's talk about sharding in Kafka. So let me, there's actually one more deck I'm gonna run through right now. Just give me a second. Just trying to download it. So when Kafka removes the message when the expiration date is reached, by default, Kafka will store a message for 7 days. All right. I'm going to share another slide deck. Let's talk about topic design and partitioning. Kafka should not replace the database. Confluent will tell you that you could use Kafka as a database. I will tell you don't do that. Kafka is not designed for querying. It doesn't have any kind of indexing. You should use Kafka as a middleware. You should use it for messaging. You should use it for streaming data and performing ETL jobs, but you should not use it as a permanent storage strategy. That is not a recipe for success. Now, can you run SQL type queries on it? Yeah, if you use, KSQL or Lens SQL or run a Spark job or Apache Calcite. But really, Kafka is not a database. Don't do that. All right, so let's talk about topics and partitioning. It should be interesting. So Kafka topics are broken up into partitions. A record is stored on a partition, usually by record key. If a key is present and round robin is missing, the record key is by default determines which partition a producer sends the record. Kafka uses partitions to scale a topic across many servers for producer writes. Also, Kafka uses partitions to facilitate parallel consumers. Consumers consume records in parallel to the number of partitions. Order is guaranteed per partition. And if you use a key, then all of those records should end up on the same partition. So let's talk about partitioning. Kafka maintains a record only in a single partition. A partition is an ordered, immutable record sequence. Kafka continually appends to partitions using a partition as a structured commit log. Records and partitions are assigned a sequential ID number called an offset. Chat text. What do you mean by chat text? I can read your message now. Okay. Yeah, you can use Kafka to integrate with different applications in SaaS. Look at Kafka Connect. Zookeeper without Kafka is not yet released. And I'm not sure that's going to happen, primarily because a lot of things in Zookeeper are used, like security, access control lists. We'll see. So these are the shards, MG. So partitions have different levels of sharding. So Kafka maintains the record order only in a single partition. A partition is an ordered immutable record sequence. Kafka is continually appended to partitions using the partition as a structured commit log. Records in partitions are assigned a sequential ID number called the offset. The offset identifies each record within the partition, and the topic partitions allow Kafka log to scale beyond a size that will fit on a single partition. So it's an n number of partitions. So this is sharding. Sharding is partitions. So a producer always writes to the end of a partition in a round robin style, and the offset is the reading possession. Let's talk about guarantees. So these are the following guarantees for a topic in most circumstances. Messages sent by a producer to a particular topic partition will be appended in the order they are sent. A consumer instance sees records in the order they are stored in the partition. For a topic with a replication factor of n, Kafka will tolerate up to n-1 server failures without losing any records committed to the log, right? Let's talk about topic replication. So, Kafka topics can be replicated across a cluster. Replication factor is the number of nodes in a Kafka topic is replicated across a Kafka cluster. A unit of replication is the amount of times each partition is replicated independent of other partitions in a topic. Replication factor of 1 or more, which is the default of 3, means that each replica will have a leader and a follower. All reads and writes to a partition go to a leader, and the followers are there in case of a disaster. So Kafka is a disaster recovery system by default. Yes, Andrew, the questions are being answered in Q&A. So basically, sharding is how a topic is distributed and also how it's copied. So if you look here on the screen, you have a leader partition and one follower. So broker 1 has partition 1, and broker 2 has a follower of partition 1. The same methodology works in Elasticsearch, by the way, and Cassandra. So leadership election happens via Zookeeper. So no, one message is always written into one partition. Yeah, the order is usually done by the how it's sent by the producer in general. So by default, you'd send a message in a batch of messages, and if they have the same key, they'll go to the same partition. Now, sometimes there could be lag or latency. So generally, there is 2 types of time. There's log append time, the one that Kafka adds to the record if you didn't send a timestamp, and the other is when you send the timestamp from your application. So there's different ways of reconciling it. So basically, a leader maintains the order. So this is all about how the replication performs recovery and failover. And I think we will skip. So each partition is stored in a broker. If a topic was not set for replication and a broker comes down, some partitions will not be available. Permanent data loss can occur. So let's talk about the architecture of a Kafka broker, right? Here it is. Yeah, this is good. So we have a cluster of 3 brokers, 1, 2, 3, right? We have the controller, which coordinates the work of the cluster. And then we have the architecture of the Kafka broker. So you have partition 0, 1, 2, and 3. So it's a 4-partition topic, right? We have a replication factor of 3. So we've replicated it. This is replication factor of 0 or 1, the replication factor of 3. It's on all of them, right? And we add a partition. So there's more partitions to the topic. No, the broker is the leader for partition 0. Broker 2 is leader for partition 1. Broker 3 is leader for partition 2, partition 3, and so on. Let's talk about partition balancing. So basically, every topic can have a number of partitions. Now, depending upon the number of partitions, that will tell you how many consumers the application can run. You can never have more consumers than there are partitions. So in here we have 4 partitions, which means we can have 2 consumers, and each consumer is reading 2 partitions. And then here we have a topic with 4 partitions, which means we can have 4 consumers. What do you think happens if I add a 5th consumer? What do you think would happen? Someone give an answer. It's going to sit idle. It's not going to do anything. It's an idle resource, right? That consumer is not doing anything. Now, can I read the same data in Kafka twice? Can I do that? Yes. Additional consumers is not a problem. It only becomes a problem when you have more consumers than there are partitions in a given topic. Now, these consumers are in a consumer group. So if I had 2 consumer groups, we could actually read the same data in multiple times. All right. So I think we've covered this. Let's get into, by the way, do you have any questions so far that I can answer? Okay. Let's talk about Kafka connectors. So basically, Kafka Connect is a robust application of Kafka that allows you to send and receive data from Kafka with various well-established data systems. So you can look at things like, Spark or Cassandra or Zeppelin or, various different things, and you can connect them directly to Kafka without having to write application code. This would be the best way to develop with Kafka. So basically, you have source connectors, which are responsible for pulling data from a data source. And then you have sink connectors, which are responsible for writing data to a data source. So the Connect framework is for streaming data between Kafka and other systems. It's built for reading from, let's say, a SQL database into Kafka, for streaming Kafka into like a Hadoop cluster, or streaming data to Elasticsearch, S3, or Splunk logs. Kafka Connect has benefits over doing do-it-yourself producers and consumers. One is these connectors are tested, they're robust, and they're reliable. You don't have to repeat the code, and there's no coding required. They're fault tolerant, provide automatic load balancing when running in distributed mode, and it's fast, scalable, and simple. So there are multiple connector types. There is a source connector, which reads data from a data system into Kafka as a source connector. as Kafka is a producer client internally. Then there are sync connectors, which is when you take Kafka and write it into an external system, which writes Kafka client data to a producer. So here's an overview of the various connectors, right? We have sources and we have sinks. Sources pull data from outside of Kafka into Kafka. And sync connectors take data from Kafka and write it somewhere. So there's various ways of doing it. I'm personally a fan of the Lenses built open source Kafka connectors called Stream Reactor, and they allow you to read data from Kafka into other data systems. So this is a very advanced, very friendly way of, like, let's say, reading some blockchain data or some Bloomberg data, and then taking all that data and then dumping it into a MySQL database or Elasticsearch if you want to perform searching. So today's interactive workshop is all about using Kafka with Elasticsearch. These stream reactors actually use something that's called Kafka Connect SQL, and it's actually based on Apache Calcite. So basically, Calcite is basically an industry standard SQL parser, which allows you to select queries to read data from a specific Kafka topic. And you could basically find nested fields, read Avro and JSON encoded documents, and you can write this data to various different things, such as, Postgres, Solr, Redis, Splunk, Spark, Mongo, JDBC, etc. So you don't need KSQL, you can use Calcite. Let's talk about workers. So Kafka connectors use workers. So it's a running process that executes the task of a connector. And a connector jobs are broken down into tasks so they can do the actual copying of data. Workers are processes that are running in one or more tasks, each in a different thread. The input stream can be partitioned for parallelism, for example. So Elasticsearch has a partition index and a table. So basically, a connector works exactly like a consumer group, right? Depending upon the number of partitions available, that tells you how many workers and tasks you could have on that given topic. Kafka Connect can run in multiple modes, standalone, which you should never do, or distributed mode, which is the preferred way of running Kafka Connect. Any questions so far? All right. So are people feeling confused or clarified? Trying to read the room here. All right, I'm going to do the final explanation of Kafka with pictures, with colorful pictures. Does a picture book work for you? So basically, failover of workers means that if a consumer fails to work, the rest of the data is distributed across the remaining consumers. All right. So I'm going to explain Kafka as if it's a postal service. I hope this works for you. So Kafka is composed of producers, consumers, which are then written and read from topics, and each of those topics have partitions. Kafka is fast, scalable, durable, open source, and it can be a managed service by us. But I think you guys want some pictures. So I'm going to make it colorful and a lot of fun. So we're going to build a modern day electronic postal service. We're going to send messages from A from pigeon to bee. So first you need A, which is a producer, it sends the message, and B, the consumer of the message. Kafka doesn't work like that. It's not a snail mail system. It's what's called a post restaurante. What that means is it works exactly like the general post office. The mail is delivered to the post office, and you have to go to the post office to receive your mail. And to receive your mail, you have to check the counter to ask, do I have any more messages? So how does a Kafka topic act like a post office, and what are the benefits? Well, there's disconnected delivery. A consumer doesn't need to be able to receive the messages. There's a lot less effort for the managed service, only has to do the delivery to a few locations and not a larger number of consumer addresses. It can scale better and handle complex delivery semantics. Well, let's look at how Kafka can scale as a post service. So if we had one partition meaning one counter or one shard, then that means we'd have a long queue, right? No one likes dealing with long lines. But if we had 3 partitions, that means we could break up this line into 3 parallel processing chunks. So partitions work like counters at the DMV. The more people available at the DMV, the faster they can process your data. But let's look at what goes into an actual message. So a Kafka is a message. It's called a record, and it works a bit like a letter. The destination is a topic, which in this case, we're sending a letter to the North Pole. A postmark includes a timestamp offset in the topic and the partition it was sent to. The time semantics are flexible, either the time of the event creation, ingestion, or processing time. There's also this thing called a key, which is optional. It refines the destination, so it's a bit like the rest of the address. We want to write a letter to Santa, not just some random elf. So, a topic, you write a letter to a topic. You can sometimes add a partition. And every message you send usually has a timestamp, offset, and a partition. And every letter also has some content in it, which is usually stored as a value, a key and a value. Now, Kafka doesn't care what's inside your letter. It's not like a SQL database where you have to have a third normal form data structure. It's like Mongo. You just send it data, that's it. It doesn't care, it sends it over. Now let's look at delivery semantics. So Kafka does guaranteed message delivery. So basically, before Kafka and before computers, there are these things called homing pigeons, and they would have to send the same message multiple times because these homing pigeons would get shot down or eaten by predators or hunters. So how does Kafka do messaging delivery? Well, basically, message 1 is written to broker 2, and that message is written to disk immediately. So that makes it resistant to power failures. Then that broker copies the data to the 2 other brokers. This is a replication factor of 3. So your data is copied 3 times, which are also then saved to disk. This makes it resilient to the loss of some servers. So Kafka can survive, 2 out of 3 server failures in most cases. Finally, the producer gets an acknowledgement that the message is persisted and replicated across the cluster. So this means that the producer will send a message to Kafka, and Kafka will tell the producer, okay, I have your data and I've copied it 3 times. It will tell you that. And you can change it. You can have it just say, have the first broker tell you if that's good enough. Now let's look at delivery semantics. Who gets the message and how many times are the messages delivered? So Kafka is a publish and subscribe system. What this means is it's a loosely coupled system where the producers and consumers don't know about each other and don't really care about each other. So you have producers over here and consumers over here. So now we are filtering on which consumers get messages and is topic-based. Producers send messages to topics. Consumers subscribe to topics of interest, such as parties. When they poll, they only receive messages sent to those topics. and none of these consumers will receive messages sent to the work topic, so no one's reading the work topic. So basically, Kafka works like Amish barn raising. Partitions and consumers share work across multiple consumers, and the more partitions the topic has, the more consumers it supports, right? Kafka also works like the clone army. It supports delivery of the... Yeah, you're gonna get the handouts, don't worry, that gets emailed to you. So Kafka, and this is also recorded, by the way, so if you want, you can watch me on YouTube. My crazy quarantine look going on. So Kafka supports the delivery of the same message to multiple consumers with consumer groups. Kafka doesn't throw away messages immediately once they're delivered, so the same message can be delivered to the same consumer groups. Consumers can subscribe to parties are allocated partitions. When they poll, they'll only get messages from their allocated partitions. So this enables consumers in the same group to share the work around. Each consumer only gets a subset of the available messages. Multiple groups enable message broadcasting. Messages are duplicated across groups as each consumer group receives a copy of each message. So how do we know which messages are delivered to which consumers? Well, the final aspect of delivery semantics is to do with message keys. So if a message has a key, then Kafka uses partition-based delivery. Messages with the same key are always sent to the same partition and therefore the same consumer. And the order is guaranteed. But if the key is null, then Kafka uses round-robin delivery. Each message is delivered to the next partition. So let's look at a concrete example of two consumer groups. We have nerds and we have Harry. Group 1 is nerds, this is about 6 consumers, and group 2 is Harry, which is a single consumer, subscribed to about all the partitions. So we're gonna look at a case where there's no key. Each message is sent to the next partition and all consumers are allocated to that partition will receive the message when they poll next, right? So Bill is reading partition 1, Jenny is receiving partition 2, and Chewy is receiving all the partitions. So let's say we're not having a key at all. So both groups subscribe to topic parties and there's no key. So you have the pool party invitation. So the pool invitation, basically Bill and Chewy, since they're reading that partition, both get a copy of it. Now you get the pool party is canceled, and that is going to a different partition because no key was used. So that message went to the next available partition. Jenny got the cancellation, Bill got the invitation, and Bill goes to a pool party all sad and alone and discouraged. So how could we fix this? Well, what if we introduced keys to our messaging? So here we assume that the message title is the key, which is pool party. So now pool party should be going to Bill each time, right? So Bill receives the invitation and the key is pool party, therefore it goes to Bill. Next we have a Halloween party. This one's going to Jenny, and that's also going to Chewy, and they have a very good time. Finally, there's event reprocessing. So Kafka stores messages on a disk so consumers can go back and request the same messages they've already received, earlier messages, and ignore some messages, etc. This is a UML diagram of Kafka. So basically, you have the producer, which sends the record to a Kafka topic, which can have multiple partitions, and those partitions will have replicas, leaders, and followers. And these partitions are stored on a broker, and brokers form a cluster. Consumers subscribe to a topic and read from partitions, and they form a consumer group. All right, any questions about Kafka? Just about concludes Kafka. All right. So why don't we pause for a 30-second. Oops. Consumers subscribe to a topic and then they are assigned partitions. The consumer doesn't actually have to know how many consumers are in a topic. It just helps. Yeah, they don't actually need to know how many partitions are in a topic. All right. So we're going to pause for about 3 minutes, and then I'll move to Elasticsearch. So I'm just going to take a 30-second break. Stick around. All right, we're back. We are back from outer space. Now let's talk about Elasticsearch. Sound good, everybody? So why do I get so excited about Elasticsearch? Let's tell you what you need to know about it. So Elasticsearch is an open source distributed search engine and analytics engine built on top of Lucene. So, think of Kafka as your boring freeway and the highway. Think of Elasticsearch as your, as your camera and the data, really. That's what it is. It allows you to make sense of data, really. You can visualize things quickly. You don't have to become a JavaScript engineer to make visualizations. You can just drag and drop elements. I mean, it's pretty nice. And you can publicly serve these data sets as well. So you can ingest all your data into Kafka, do your data transforms into Kafka, and then create a focused and narrowly scoped data set in Elasticsearch. So Elasticsearch is an open source distributed search engine, which can read anything, log files, messages, config info, documents, and lists. And it's a RESTful API. And all this data can be outputted for application monitoring, search, security info and event management, and infrastructure monitoring. So Apache Lucene was an open source project, a search library written in Java. Allows full text search, and it was challenging to use, and Lucene wasn't designed as a clustering technology. So Elasticsearch was built on top of Lucene to be more scalable and easier to implement. So what are the use cases of Elasticsearch? Basically, you check for errors today, early in the morning, between 3 a.m. and 6 a.m. And how do you find the multiple errors from thousands of system log file lines, right? So you have all these log errors, you need to make sense of them. So you should use Elasticsearch for logging and log analysis, network monitoring, business analytics, security analytics, full text search, enterprise search, geolocation, and autocomplete features. I also use it for pattern recognition and finding different things in your data sets. A lot of large, yep. So Yeah. So basically, you can use Elasticsearch for log and log analysis. So we use it for monitoring our fleet, our security, and our safety. We also have network and security monitoring at LinkedIn. Facebook uses Elasticsearch for their enterprise search, and SWAT.io logs S3 files with their monitoring featured. The other feature of Elasticsearch is what's called security analysis. So Elasticsearch allows you to centralize and analyze events from across the entire organization to enhance incident response and to monitor that threat across the applications and the system in real time. Then you have app and database monitoring as well. So Elasticsearch allows you to monitor database hotspots. The usage of Elasticsearch is growing quite frequently. In this case, it's about 10% or so. That's quite a lot in 6 months. What are the benefits of Elasticsearch? Scalable, full text support, RESTful API. It's a distributed technology. You have autocomplete search, fuzzy logic searching, fast search, document-oriented, schema-free, and multilingual support. Elasticsearch has many benefits, true. It's very scalable, it's a RESTful API, and there's a distributed approach. It's designed to scale horizontally because it's a sharding technology like Kafka, so it also has partitioning. Elasticsearch provides a RESTful API for communicating for cluster over HTTP, and Elasticsearch is designed to be distributed in multiple nodes. Elasticsearch features full text search, such as splitting words into customized stemming, faceted search, etc. It has autocomplete and instant search. So Elasticsearch completion suggester provides autocomplete and search as you type functionality. Fuzzy searching. You can find what you're searching for even though you have a spelling mistake. Elasticsearch benefits. It's multilingual. Multiple languages work with Elasticsearch. It's optimized around full text search and even very large data sets, and it's designed for JSON type documents. So it uses JSON notation, and that is its serialization format as well. So all the data is in fact stored as JSON. Different Elasticsearch use cases. So you have IT operations, application management, and security analytics, marketing insights, business development, and customer sentiment. So you have metrics analytics, operational analytics, then you have application search URL, so website search and application search. You have internal systems and applications and external systems and applications. So at the bottom, you'll see security operations, developers, architects, IoT, business analytics, leadership, and HR. There are other technologies that it's a JSON only format, I think. You can probably ingest other formats into it using converters, but it is stored as JSON. So Splunk is a proprietary solution, pure and simple. It has its own processing language, Splunk processing language, its own RESTful interface. It's more expensive. Its index storage are flat files. So Elasticsearch is also flat file based, but I think both are JSON. The indexing technology in Splunk is C++, so naturally it will be a lot faster than Java-based Elasticsearch. Splunk has its own user interface, and the search technology is a MapReduce method, and Elasticsearch is built on Lucene. So let's talk about Solar, because that's a very interesting technology. So Solar is the Apache Foundation, and Elasticsearch is its own company, but there is an open distro, and we'll talk about that later. Node discovery. So Solar uses Zookeeper, which is mature, battle-tested for a large number of projects, and Elasticsearch uses Zen. Shard placement. So Solar is static in nature and requires manual work to mitigate shards, starting from Solar 7. Elasticsearch is dynamic. Shards can be moved on demand depending upon their cluster state. Caches are global and validated with each segment change. And Elasticsearch is per segment for better dynamically changing data. Analytics engine, facets and powerful streaming aggregations, and Elasticsearch is sophisticated and fully flexible aggregations. Query execution. You can't really optimize Solar queries. Elasticsearch, if you change your context and indexes, you can make it faster. So basically, Solar is optimized around static data sets because of caches and its uninverted reader. Elasticsearch is very good for, a live data sets because it has a per segment caches. So every time it has a segment of caches, those caches increase over time. Let's talk about full text search features. So Solar is a language analysis based on, so they're both based on Lucene, basically. So they do have full text search. So Solar does not really appear to be DevOps friendly. Elasticsearch is DevOps friendly. Non-flat data handling. So they both support nested documents and parent-child support. And the query language in Solar is much more flexible. So Elasticsearch is JSON querying only. Solar apparently works with XML, URL, and JSON. However, the searching queries are limited. Indexes. So leader placement control and leader rebalancing is possible even on the loads, and you can't really do leadership election with Elasticsearch. You have a master and slave kind of architecture with Elasticsearch, or sorry, primary and secondary is a politically correct way of saying that. Machine learning, both of them support machine learning. So let's talk about the differences of Elasticsearch and a relational database. So Elasticsearch is a NoSQL data store. Elasticsearch has no relations, no constraints, no joins, and absolutely no transactional behavior. And it's easier to scale compared to a relational database, right? Relational database is designed to work in a single database, a single machine, and you have to put everything in third normal form. And yeah, I mean, you could query like a secondary cluster in MySQL, but it's a vertical technology. You really can't have like a MySQL cluster of 3. Like even Vitesse is like not really a distributed. The main difference between NoSQL and a database is NoSQL technologies are designed by nature to be more scalable. So Elasticsearch is a index, it's document in the field, and a database has tables, rows, records, and column names. So let's look at use cases where database is not well suited. Relevance-based searching, searching when entering spelling that a search term is working, full text search, synonym search, phonic search, or lag analysis. So let's look at the history of Elasticsearch as well. So Elasticsearch was built in 2010. 1.0 was actually released in 2014. Version 2 came out in 2015, and so on. And then in 2019, we have an open distro of Elasticsearch. An open distro is basically a majority of the proprietary features are now pure and open source. So you don't have to pay Elastico a license to use a lot of the proprietary features. So let's talk about open distro for Elasticsearch. So Apache OpenDistro is an Apache 2 licensed version of Elasticsearch enhanced with enterprise-grade security, alerting, SQL, and more. So the benefits are it's 100% open source, so you can change it, do whatever you want. It's enterprise ready, so you can do SQL queries on it, and it's community driven. So it provides individuals and organizations the freedom to contribute changes to the distro. So let's look at OpenDistro and the ELK stack. So basically the benefit of OpenDistro is you have alerting, you have authentication, you have access control, you can encrypt your nodes, you have security integration like Barrows, LDOP, machine learning is built in, you can do SQL type queries on OpenDistro, which is very useful if you're doing some data sets. You can also do JDBC out of the gate with OpenDistro. So if you have a database, you can connect your search results that way. And you can also monitor it. There is good documentation and forums. So what is Elasticsearch? Like, what's the technology behind it? Well, the ELK stack consists of 3 open source products: Elasticsearch, Logstash, and Kibana. Elasticsearch is a highly scalable search index engine. Logstash, which is a tool for collection, enrichment, filtering, and forwarding of data. We're using Kafka Connect in place of Logstash. And Kibana is the thing I really like, which is a visualization tool. So we'll be looking at that in a few minutes. Basically, you would input your data through Logstash, which would collect the inputs, filter them, and output them to Elasticsearch, which stores data and indexes it and processes queries. And then you would put Kibana on top of Elasticsearch so you could make sense of the data. So Kibana, you can discover the visualizer dashboard, which runs on the browser and builds queries. So Kibana is a visualization engine, and it allows you to do things. So let's understand how you'd actually insert data into Elasticsearch. So a document is a basic unit of information that can be indexed. Documents are serialized into JSON and stored in Elasticsearch. Elasticsearch has a generated ID and is provided manually. Some examples of a document are a log file, a tweet, a metric or a value, a blog post, a comment made by a customer on your website, a row in a CSV file, and a weather details. Now, a document is never a list. A document is a row. That's kind of the most important thing to realize when you load data into Elasticsearch. You need to filter it in some way. So a document example. So a tweet needs to be converted to JSON. So each tweet of data represents a single document, right? So basically, here's a tweet from our company. Elasticsearch is the most popular search engine and also the top 10 most popular database management systems. And you take that raw tweet and you convert it to JSON, right? And when you convert it to JSON, then you can load that into Elasticsearch for searching. And the JSON document consists of field and values. So I'm assuming everyone here is familiar with what JSON is. JSON is basically a data structure. It's like XML where you have keys and values. So you have username, Instacluster, tweet, which is the tweet, and then you have the date. It's very important that any record you send to Elasticsearch has time. Just like with Kafka, you always need time. It's very important for making sense of the data later. So each tweet needs to be converted to JSON, and each tweet of data represents a single document. So this is a CSV. So basically you take a CSV record and you convert it into JSON, and that JSON can be loaded by Elasticsearch. So you have your CSV row, some application converts it to JSON, and then it's sent to Elasticsearch. So Elasticsearch is an index. It's a collection of documents that have somewhat similar characteristics. An index has some data schema mechanism, also called mapping. And index data is distributed across an Elasticsearch cluster. You should always have a timestamp in general. You need timestamp for ordering for sure. So your index data is distributed across a Elasticsearch cluster, right? So here you have a 2-node Elasticsearch cluster and a logging index, right? So node 1 is a production cluster. You have shards, and you have primary and secondaries. So your index is copied across multiple things. So first you have your JSON document, which goes to the logging index. The index name, it's like a route on the server, right? Like / syslogs. And that data is then distributed to the 2-node cluster. So here you have a 2-node cluster, node 1, node 2. And each of those nodes have, in fact, 3 shards, right? Well, actually, 4 shards. So they're copied to the different shards in the system. So let's look at our tweet index. So basically here, you have your username instacluster. Tweet is instacluster managed service and our time. And the tweet will go to the tweet index. So it's going to go to these various different shards. And the index is distributed on multiple nodes within a Elasticsearch cluster. So let's look at an index document. So documents are indexed, stored, and made searchable by using the index API. So we use a put or a post and add the document in the body request. We specify the index, which has a type and an ID. And if no ID is provided, then Elasticsearch will generate it automatically. Each document requires an ID in Elasticsearch. If your data doesn't have an ID, an Elasticsearch will automatically generate one for us, right? So you have an index name and a document type and an ID created. You can use the get to get records from Elasticsearch. So basically you would give it the index, document type, and then the ID. And the ID would return the record. Then we also have a search API. So you search to retrieve documents from an index. Elasticsearch returns 10 records by default. And it will also tell you how many milliseconds it took to process the query and the number of documents returned from the query. We do have a full day on just using Elasticsearch, so this is what I could cover right now. I think it's time. Let me just go back to the beginning. Do you guys have any questions about Elasticsearch before we get into the lab? You could put one document in multiple indexes. It's just better to keep it in one. So the way you could use a database for hotspot detection is you would connect it to your database using JDBC and then link it to your queries so you could monitor your query performance. That would be one way of doing it. There are commercial versions of Elasticsearch, but you're going to be using OpenDistro, which is just as good and it's free. There is a machine learning option with OpenDistro. Let me just go over the features of OpenDistro if you don't mind. So just give me a second here. Just trying to find my Zoom. So I'm going to cover the features of OpenDistro. So what is OpenDistro? So OpenDistro allows you to, I don't really cover querying today. That will be another workshop with Elasticsearch. But basically, it allows like security, and you can do SQL queries on the data sets in OpenDistro. That's not covered today, unfortunately. And you can do performance analyzing and query monitoring. So OpenDistro features things like encryption, authentication, role-based access controls, multi-tenant environments, and audit logging. So if you're in a highly compliant organization, OpenDistro is also completely open source. You don't have to pay a vendor for any of these features. So most vendors would tell you, hey, you have to pay for this. OpenDistro was made by Amazon. It's a very good thing. So they don't charge anything for it. There's different security concepts. You have users, so you can authenticate with it. You have roles, so you can do different permissions on these indexes. You have action groups, you have backend roles and role mappings. So you have different levels of encryption. So you can do input files, messages, metrics, logs, etc. And then you can visualize it all in Kibana. So authentication. So OpenDistro allows you to do very basic HTTP authentication, authorization, permissions, and action groups. So you request your credentials and you get authenticated. OpenDistro also has role-based access and controls. So you can do document level security. If you have sensitive data, you could limit access to it. You have field level security, inclusion, exclusion, and cross-cluster search. So you could search multiple clusters. Additionally, Kibana is a multi-tenant solution. So you could have one Kibana to rule them all. We have flights, records, logs, and e-commerce, and you can have different pages. So tenants in Kibana are spaces for saving index patterns, visualizations, dashboards, and other Kibana objects. Tenants are useful for sharing data of your work with other Kibana users. By default, Kibana users have access to tenants, private and global. A global tenant is shared between every Kibana user. A private tenant is exclusive to each user and can't be shared. Let's talk about cross-cluster searching. Cross-cluster searches enable you to search a cluster to execute queries against other clusters. The authentication flow. So when accessing a remote cluster from a coordinated cluster, you don't have to. So you can basically search multiple clusters. Audit logging. So you basically have the ability to track all actions performed by all users in your Elasticsearch cluster. So any failed logins, SSL exceptions, bad headers, monitor suspicious activity, and you can set up alerts as well. And this allows you to be compliant with things such as GDPR GDPR, HIPAA, PCI, and ISO 200. Alerting features. You can create monitors, like in the dashboard. You can set up alert thresholds, and you can set up webhook integrations, so your open distro could integrate with Slack and webhooks. So this is kind of where open distro becomes very valuable. So instead of using Grafana and Prometheus, you could just immediately do pattern recognition and set up alerts that way. And you also have the ability to view alerts over time. So you can view things like infrastructure, application monitoring, Docker monitoring, and security. And you can integrate things with things like Slack and webhooks. There's also SQL support. So you can translate SQL to JSON. You can perform aggregations. So you have like this SQL board, so you can view records and take different indexes and query them together. That's not included in today. I'll be updating the code to show you the SQL. Well, I actually have the SQL query in the screen, but we won't be testing it until later. You have a performance analyzer, so you can look at your various different SQL features. And you have I have top in Linux, so you're able to look at the various operations and how well they're performing. Index management. So OpenDistro allows you to monitor and automate index management. There's index state management, which allows users to define unlimited custom policies to be applied to routine tasks on indexes and move indices from one state to another. You can keep track of operations, and you can apply policies to those indices like read, write, merge, etc. There's some new features in development like machine learning algorithms, anomaly detection, and performance and root cause analysis. So let's cover OpenDistro for Elasticsearch and Elasticsearch. So like I said, OpenDistro is fully featured. In today's workshop, we just have the open source ELK stack, so there's no SQL support. I'll be updating the code later this weekend with the SQL support, so you can run some more queries. And I think that's all there is to, yep. So to answer your question on commercial versions of Elasticsearch, just don't pay Elastico. Download OpenDistro, it's free, it's open source. It was made by Amazon to compete with Elastico because they needed a non-proprietary solution. So we support OpenDistro, Amazon supports OpenDistro, and you don't have to pay a license. And it has all the nice features you want, like role-based access and controls. All right, are you guys ready to do a lab? You guys ready to do some stuff, do some code? Are you excited? All right, let's do it. So we're going to do 2 lab exercises today. We have an hour and a half remaining. So let me just show you what we're doing today. So if you remember, in fact, I'll try and put it in the, here, let's put it back in the chat room. Now is where we're going to do this, okay? So if you haven't set up your Docker yet, do it now. So we're not actually going to use Cassandra, but I am keeping it in here just for now. So basically, you would use Cassandra as a distributed database. We're not really using it today, but it's included anyway. There's no Spark included today. I'll probably add it later. Today is all about Kafka and Elasticsearch. That's all I'm focusing on. So what we're going to do is we're going to take the world clock time, download it into Kafka, and then put it into Cassandra and Elasticsearch using Kafka connectors, which are pure open source. You don't really have to do much of anything. So let's look at how event-based data modeling works, right? Well, first of all, you have to think about the problem you want to solve, think of the input, and then you think of the output. So think of the output. I want to see if there's a correlation between Trump's travel and his mood. So you could think of the input, right? Well, where could we get his travel plans and where can you find his mood? What's the #1 source of data? I can't really think of anything. Can someone tell me an idea? I don't know. Something. Twitter. Pull that data from Twitter. So we're going to pull that Twitter data from Kafka and put it into a Twitter topic. If you would partition the data based on a partitioning key, you'd perform a sentiment analysis and a mood analysis based on each of those tweets, write those results to a file, and then you have your own data flow. So that's how you would use Kafka. What about Elasticsearch? Why would you use Elasticsearch? Well, Elasticsearch is all about those visualizations and prediction models. So use Kafka as your boring freeway, use Elasticsearch as your cool, fancy rocket ship to make sense of all the data. Or really, I would just call it your sports car or your SUV, depending upon what you're trying to do on the road. So Elasticsearch is a very powerful engine for making sense of data. So you do your web traffic. You can make sense of it this way, and it allows you to build a rich user interface. All right, so let's combine all these technologies in today's first example. We're going to use a REST API to pull some data. We're going to copy it into a Kafka topic and then write it to both Elasticsearch and Cassandra. All right, guys, do it. Just do it. Open up README, and you can follow the instructions that way. I want you all to do it. I'll give you 15 minutes, and then I'll perform the exercises, and I'll start helping people. Sound good? Awesome. This is interactive. I need you guys to do this. Is anyone going to download the code or respond in the chat? All right, 15 minutes. Check it out. I'll come back. You get it working, Jayesh? Rich Capsy still downloading files. It shouldn't be that many. I mean, Docker would take more time. Awesome. So you're just downloading the stuff. Yeah, you follow the instructions in the README. So here. So git clone. So in case anyone doesn't know how to use git, I don't know what to tell you, but you got to clone the copy base first. You got to make a jars directory in the code base. It works for me on Mac OS. I mean, that's what I'm using. Yeah, wget will work on Mac OS. You might have to do, brew install wget. If you haven't downloaded wget, then you have to turn on your Docker. Docker compose up. extend it 5 more minutes, and then I'll just walk through it. You just need to download the jar files. You don't have to use wget. I mean, if you were just to take, you can just copy and paste these into your browser and download them that way. Look at the readme.md. You have to look at readme.md. You'll see a lot of exceptions on the Kafka connector. Don't really worry about it. Just try to get the connectors on. Wait about 5 minutes and those errors should go away. All right, so everyone can see my screen. Let me just share my screen here. Share terminal, yep. So, there's my jar folder. It looks pretty good, I think. Basically, we want to download these jars. Then we want to do Docker compose up. So let's just do that. No. Here we go. So, yeah, Juan, you don't have to use wget. You just have to download the jar files. So you could do curl L. So here I'll go to cd jars. Yeah, like let me do it here. You can do it this way. There you go. You can download it that way. So if you don't have wget, then you can download the jars that way. Or you could just, click on the link. Okay. So I have the jars downloaded. I'm just going to turn on my Docker. So everyone, after you download the jars, you should be doing this. Yeah, I can increase the font size. Gosh, I don't know how to increase the font size here. So don't worry about all this text. Just wait like 5 minutes, brew some coffee, I don't know, let it turn it on. You don't really have to worry too much about what's going on here. So it's turning on Cassandra. These are all the error messages I told you not to worry about. Basically, it's expecting some other jar files which we're not using. So that's why it's going to throw all these error messages. Yep, more error messages. But we're not using it, so it doesn't really matter. Could be pretty annoying though. Okay, so you see how it says finished starting connectors and tasks? Good, right there, it's all finished. Bingo, good. Now the fun part. So, next thing we want to do is we want to download the REST connector. So this is a Kafka connector. So the way you interface with Kafka connector is basically you want to run a JSON file. So I've turned on the connector, and I'm just going to explain this connector a little bit. So what do you see here? You see a bunch of things, right? You see that, well, first of all, it has this API. So we have a connector, it's a RESTful interface. Okay, fine, I'll do command ++, have it better. You can all read now, right? Hopefully that's good. So every Kafka connector is configured in JSON. Yes, Sunny, you have to be in the folder directory. Do you notice the path I'm in right now? I'm in the open source project. So yeah, it's okay, Sunny. We all are learning. This is the time to learn. So that's the configuration. We've started to load the JSON data. And let's just check that we got the data in Kafka. So we can run that over here. So what this will do is it will turn on a Kafka consumer. It's going to connect to Kafka. Yep. No, damn you. Trying to make it bigger. There we go. So it's going to read some records. Should read a few anyway. Okay, cool. So it's reading some records. Not too bad. So it's getting the world time. Cool. So now I'm going to do the next thing in the exercise. What does it say to do? Yeah, you copy and paste them one at a time, Richard. So you just copy and paste them one at a time. You don't just copy and paste all at once. So we're going to turn on the second connector now. This is going to write the result to Elasticsearch. Okay. And we can validate if the data is in Elasticsearch by just running a curl command. Because remember, Elasticsearch works like that. Now, if you want, you could Cassandra, but it's not a focus of today's workshop. Okay, so that looks like the data's there, right? That has data. If data's there, it's there. Cool. And we can run this again. We should get, yep, we should get. So every 1 minute, it's going to give us another date time. Well, you saw what I did, right? I'm just copying and pasting one command at a time. I'm not doing anything crazy. Okay. So then we can do another thing. We could turn on the Cassandra connector, because why not? Well, let's just skip Cassandra because it's not at all used in this workshop. Let's examine the Elasticsearch connector. So let's do clear. Should be okay. So this SQL you're seeing here is actually called Kafka Connect SQL. So it's based on Apache Calcite and it allows us to do entity extraction. So what we're doing is we're making sure the data we send okay. So this is the configuration of the Elasticsearch sink. So basically what we're doing here is we're taking the data in Elasticsearch and we're taking the world time, we're putting it into Kafka, and then we're dumping it into Elasticsearch. So now what we're going to do is we don't need that one. We want this one. Okay. So this is Elasticsearch, and we need to build an index pattern. So you go to index patterns. You should all have it running right now, by the way. Go to localhost 5601, and you can have a lot of fun. So let's look at our index patterns. We're going to create an index pattern. Oh, cool. We already have one. Current date and time. Current dash date time. Yep. Click next step. You need to select a time field, and you've created your index pattern. Then you go here to explore the data. And cool, you have some records here. And if you want, you could start adding this to the chart. So let me just go back to the slides for a second. Right? Oh, come on. So you check out the code base. Very good. Elasticsearch is there. You want to install the binaries. Now you can just download them. Now remember to read the README file, turn on your Docker. You want to turn on the REST API first. This is what your REST connector looks like. You want to examine the topic data. So your data is really going to look like this, right? You have an ID, you have a current date and time and all this stuff. Now, the first and most important thing in any kind of data science or any kind of prediction modeling is you have to clean your data. So if you wanted to load this raw JSON into Elasticsearch, you would run into issues. First, because that ID value would throw an Elasticsearch exception. So we have to filter out this data entirely. And then there's a bunch of other things like Booleans, like null values, like Elasticsearch might not like that. So if you notice on our not that one, the Elasticsearch connector. What are we doing here? Well, we have a SQL statement, right? And this is what it's doing. It's selecting entities. Yeah, nothing's going to run when you run. Docker is your machine environment. So basically, what Docker does is Docker is like your lab. So all the machines turn on, you know, Cassandra, Kafka, Elasticsearch, so you don't have to do anything. Then what you do is you want to enable the Dockers, and then eventually later today, we're going to run the Python commands as well. So our Kafka connectors here are basically extracting field entities from the data. And you can validate your data, and you can also just look at the entries here. Has anyone managed to get it working? So see how it's a live data set and you're able to look at it. Once the data is in there, you should be able to play with it. Rich, what you need to do is you need to run the curl command differently. So instead of wget, you're going to run the command like Craig put up there. So Has anyone been able to get anything working? Okay, don't worry about Cassandra. It's not at all used in this lab. Yeah, Rich, look at, oh wow, you're waiting a long time. Wow, I guess, sorry about that, yeah. Craig, that looks good. No, just wait for everything to finish. I was kind of hoping by this point you guys would have turned Docker on when we started, but it's okay. We have about 40 minutes. Yeah, 40 minutes. Let everything run. Open new tabs, by the way. You should be running these curl commands and wget commands in different terminal windows. You just need to paste them one at a time. You can't just copy all of them at once. It won't work like that. Each of those commands you need to run one at a time. I'll put the modified commands. Rich, I'll show you in the group chat, okay? All right. Yeah, usually wget works for me. I was not aware that that would be a problem. Oh. All right, so I'll replace it with curl. I've already saved it and I'll push it. All right, so I think yeah, Ram, you have to wait until the Docker connectors are running. I don't think they're running yet. You might have to wait a few more minutes. Check your so see here, clearly it's running. It's committing offsets. Check that your connector Docker log is running. Wait, why is it paused? Resume share. Why is it? Okay, now you can see the screen, I hope. Can you see my entire screen? And really don't focus on Cassandra. We're not using it for the second part of this lab, which is looking at COVID data. Are you guys ready to do some data processing with Corona data? Sound good to everybody? All right, well, I'm eager to show you some COVID-19 data. So now, you're gonna look at a different file. There's a file here in the folder, COVID-19.md. Open up that file. Yep. There you go. So open up that file and follow the instructions. Rich, try the connectors again. It should work after a certain point. So to pull in the COVID data, here, couple things we have to do here. Is everyone ready to move on to the next subject? Can everyone see my screen? I need some answers in the chat room. Okay, cool. So we're gonna use Kafka to process the data, and we're gonna do some event-based data modeling. So basically what we're gonna do is we're gonna have two Kafka pipelines running. Okay, Rich, what you could do is you could literally just copy and paste each of the links, put them into your browser and download them, you know? And then put them into the jars folder. So you don't have to run curl, you don't have to run wget. It's in the README. So next to wget command are the links. So you would download like these files, you know, all of them, you would just download them. But anyway, so what we're gonna do is we're going to process COVID-19 data. So basically what we have is we have two workflows. One is we're gonna pull some data from, you know, the government. Then we're going to clean the data using Python, and then we're gonna sync it into Elasticsearch. So basically the data we're getting is all the global data worldwide with COVID-19 data, and we want to format it in such a way that we could process data. So right now, Elasticsearch doesn't like giant chunks of data. It likes to have row-based data. So we have to convert this giant export of data into a stream of data. So what we do is the clean data will look like that. We'll also correct the date format as well. Similarly, we're also writing a data pipeline for stock market volatility. I'm actually kind of curious to see if there's any kind of correlation between volatility in the market and, you know, the number of cases going on in Corona, right? Wouldn't that be an interesting thing? Yeah, Sunny, I don't think your Elasticsearch is running. You need to turn on the connectors first. So Sunny, I'm just gonna reply to you privately. So basically our stock market volatility data is going to look like this. Again, Elasticsearch doesn't like giant bulk uploads of data. It likes streams of data. So we have to convert a bulk upload into a stream of data that we can process. So we're going to combine all these technologies and we're going to do our data processing in Python and SQL. So open COVID-19 and follow the instructions. So first, I'm going to ingest the corona data. Right, wouldn't that be good? So this is going to turn on my corona data. Can everyone see my screen, by the way? Okay, cool. Then I'm going to load the volatility data. This is stock market volatility. So now we should have two data sets. Okay. So you're going to make this dot rest. There we go. So to pull the volatility data, you actually have to run this command. And that's a mistake. I need to fix it. I really apologize for that. It's COVID rest. There we go. So we're pulling the data. That's pretty cool, right? So now we're just going to confirm that we're getting the data into Kafka. So this is kind of, data science 101, right? Let's just turn this search off. So I'm just going to check the topics. So all the COVID data should be going to this topic. It's like megabytes of data. Okay, there it is. So it's in Kafka. We have all the cases. Cool. Done. Let's do the same thing with our volatility data. So we're going to check the other topic. Let's make sure we're downloading it correctly. Now remember to use the command in the webinar chat room. So this is going to be fix. Yep. So now we have our stock market volatility data going back all the way to 2004. So we have a lot of data. Is everyone with me so far? All right, I'll just assume you're ready. So now let's do the fun stuff. Because this data is pretty cool, right? But we can't really do anything with it because we have to normalize it. Elasticsearch can't read dumps of data. It needs records. Like a database, you have to insert one row at a time. Same thing with Elasticsearch. So what we have to do, I hope everyone can see my screen. So first, we're going to clean up the COVID data, right? So here, I'll just make it very easy for us to all understand what's going on here. So basically wrote a very simple Python program. Super, super, super simple. Maybe I can do syntax highlighting here. Hold on. Yeah. You just make this bigger text. How do I make it bigger? Oh, come on, I just want to make this bigger. There we go. Okay. That is a hello world of Kafka for data science, right? So what's happening is you're importing your JSON because we're going to process JSON data. You have date time because we have to format the data in such a way that we could cross query the data, right? Then we have our consumer, Kafka consumer, which reads from the topic COVID-19 global data. We're only pulling one record because this is one data set. Now, the interesting thing about this connector is it will only run once every 24 hours. So it's going to ingest data once every day, and once every day, it'll get a new giant subset of data. And then it will update Elasticsearch with the new records, but that's something later. So we connect to Kafka. This is our Bootstrap server list. I also threw in this little thing here. Basically what this is doing is it's making sure that the consumer is always reading from the beginning of all the records. I don't really want an offset for this application. Next, we have our producer. Our producer is basically going to connect to Kafka. It's going to serialize the data in JSON. Now, why is it doing it in JSON? Well, because Elasticsearch needs JSON data. So Kafka is encoding the data into JSON. So if this is confusing, I do apologize, but basically this is ensuring that all the record dates are properly formatted in a format that Elasticsearch likes. So Elasticsearch wants a format year, then a dash, then month, then day. And we update the records accordingly. So that's our COVID-19 data parser. Now let's look at our VIX data cleaner. So if you've used different programming languages before, some platforms don't like white spaces. Just for the point of sanity, I've cleaned out the white spaces. And what we're doing here is we're pulling all of the VIX records. Again, it's one giant dump. And there's a little Boolean here. It's very important. What is that doing? So basically, it's checking that the year today and the year in the record are the same year, because we don't want stock market volatility records from like 2004. That's not useful to us at all. So what we're doing here is we're actually filtering out all records before 2020, because I'm not very interested in viewing stock market records before 2020. So we're filtering that out, and we're sending the data to a topic called VIX clean. So the data's been cleaned. And similarly over here, we have another data called COVID US. So right now, I'm just looking at a subset of American data. I'll be updating the code over the weekend to look at worldwide data, so we could see if there's a correlation between, the number of confirmed cases worldwide and stock market volatility. There's an obvious correlation, but it's pretty interesting just to look at this. So, how do I get out of full screen here? Exit full screen. There we go. Okay. So let's see. So we're going to run our Python scripts. They're pretty neat, right? No. Okay. So we just need to run them one time, Python 3, COVID-19 data cleaner. So this is what the data looks like that's going into Python. Now we can validate this data by just checking the topic to make sure it's going the way we expect it to go. So I'm going to run in another tab and just it's going to validate it over here. Yep. So our records are there as we expect them. That's good news. 447 messages. Pretty neat. So that's running. We can just kill it. Next, let's run our other data scrubber. So this will be our VIX data cleaner. You notice that the format of the date has been corrected. So that's running. That's good news too. Okay. So let's check that set of data to make sure it's there in Kafka. So we just checked our data there. Let's go check the data here, VIX clean. Okay, the data's in there and it's been scrubbed. Now, all that I've really done is I made sure that the date formats match. So initially, the dates didn't have these zeros in front of the 5. So if you ever tried to cross query them, the dates wouldn't match. So you couldn't do a cross query. Okay. So yeah, I'm gonna, yeah. So yeah, requirements.txt would be good. For now, it's just standalone. You run it on your laptop and connect to the cluster. So the next thing we want to do is we want to send the data to Elasticsearch. So what I'm going to do is I'm going to send this COVID data to Elasticsearch. So here we go. Okay. So the data should be in there now. Run a curl. Should be creating the, there it is. So we have an index. Pretty cool. So now it's in Elasticsearch. Neat. Let's get our data, our volatility index into VIX. I'm just going to quickly delete the connector. Okay. So we do VIX elk. There we go. All right. So we're not running VIX Rex, we're running VIX elk. So VIX elk, that should write it to Elasticsearch. There we go. So now it's in Elasticsearch. And we need to just validate that that data is there. So we're going to do is we're going to just check the index. Going to Vix elk. Should be like this. So we go like this. Okay, so our stock data is in there. So now the big moment. Let's do some fun stuff, right? Why don't we start doing some stuff with this data? So let's go to Kibana, index patterns, right? So we have a couple index patterns. We have the COVID-19 US. Got it our time field, it's very important. So we're creating two index patterns. We'll create another index pattern. We'll call this one VIX. You always have to select your time field. All right, cool. Let's start visualizing our COVID data. And we're going to show the dates from, let's say, 4 months ago. Awesome. So we have a lot of stuff here. A lot of stuff. I want to add the field confirmed, deaths, and recovered. That looks good. Just save that as all right. Let's look at another index pattern called VIX. And I want to add just VIX and the date. So VIX is the index for stock market volatility. So basically, do VIX. Okay. So now let's build a dashboard, right? So what you do is you go to add existing. Can we all see my screen, by the way? I just want to make sure. So let's add the COVID data. And we want to add VIX. Okay. And then what I want to do is I want to look at the beginning. Well, we should be able to update both of these at the same time. So let's see if we can do like last 90 days. Yeah, there we go. Okay. Let's go back to the beginning. So in the US, there weren't really many cases until March when you look at the data sets. So volatility index is kind of normal here. Then it starts spiking around March, right? I mean, just look at that, it's in March. So let's get to March and the numbers just get really, really bad. Yep, March. So we're starting to see some deaths. And if I included the data sets from like, China and Europe, they were really bad in February. So that's why the volatility index is much higher here. But if we go into like April, yeah, like around here. So this is when we had about 100,000 cases in America, March 29th. Okay, so let's look at April 12th, because that's like peak. That's when things started actually locking down, right? So stock market volatility index, April 12th. Yeah. What's interesting is the market volatility went down. I think if we all recall, March is when the stock market went on a free fall. And around April, when all the lockdowns happened, the stock market wasn't really collapsing anymore. So market volatility kind of held stable during the actual crisis. So it's interesting, if you look at June, the volatility has gone down. And then if we go to June up here, you're able to see some interesting trends, right? So you see there's kind of like a flat line. The number of deaths has only gone up by a couple thousand. You can do some stuff with KQL. I'll show you how you would run the query to join them. So basically you would join them on the key, which is date. So all of the records are stored based on date. And then you could join them. So that's the data set we have right now. Does anyone need help getting this working? Yeah, we could figure out a line chart. Do a line chart. So we gotta give it some fields here. Anyway, we can do a line chart at some point. The data's here, you can make sense of it. You can add a line chart if you want. I'll provide updated instructions on how to do that, but your data is all here. All right, any questions? Anyone need help setting up stuff? You're welcome, Craig. All right, that concludes the workshop. If you need any help, just send an email to support@instacluster.com or send me an email. My email is as follows. I'll put it in the group chat. There you go. Yeah, I'll add some more open another terminal stuff. That's really good feedback. Thank you for sharing that, Rich. I see the point to that. Let me note it down. You're right. You're okay, Berto. All right. I mean, Rich, we can keep talking. You know, you have my email and set up a time on Zoom. I'll help you out. It's totally fine. Just not today because I'm kind of tired. Guys, send me an email, zeke.dean@instacluster.com. I can help you guys out over the weekend. Just send me some emails. I'll be updating the code as well on how to open the other terminals.